Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, well, let's get started. We've given people the traditional grace period. I'm pleased today to introduce Todd Austin. Todd is a professor at Michigan in Ann Arbor. He's very well known in computer architecture and has wide-ranging interests, including compilers, hardware and software verification, and performance analysis tools. Todd has also worked at Intel, not too far away in Hillsboro, Oregon, and he's well known for creating the simple scalar simulation framework.
Well done. Blamed for that. All right, thank you. Well, it's a pleasure to visit today, and it was somewhat fortuitous because so many of my academic colleagues are here as well today. So, what I'm going to talk about today is something called better than worst case design, which is something I've been working on for the last 7 years. And it really came out of my experience at Intel, where I worked in a research lab that was doing advanced development for the Pentium 4 team. So basically things that were busted on that design we were going to address. And I got a chance to see a big microprocessor development in action. And one of the things that really struck me was that designing the thing is the smallest part of the whole process. And really, verification was really the biggest chunk of the engine that produced that design. In fact, for the Pentium 4, there were 2.5 person centuries of effort put into the verification of that design. Huge amount. And I've heard that even software verification overheads are even larger. So when I went into academia in '99, I thought, wouldn't it be cool if you could build a piece of hardware for a microprocessor that was either provably correct or could fix itself if something was broke? And that's really where this work started. What better than worst case design is a new approach to design, where the old approach is worst case design. You assume you're going to build something, it's going to work forever, it'll never have any bugs in it, it will always meet timing at the circuit level, etc. Better than worst case design says it'll almost always do these things. It'll almost always be bug free, it'll almost always work correctly, it'll almost always meet timing. And instead, the way we build the design to be correct is we add checkers to the design, which are little hardware entities that basically watch over what's going on in the design. And when the design fails, it corrects for that. It's a new approach to hardware design. And I'm going to talk about today 2 research projects which grew out of that in my work that really embody this form of design. And I'll talk a little bit about what other people have done in the years since that have been inspired by this style of design. So lots of acknowledgments. Faculty I've worked with at Michigan, Valeria Bertacco, David Blau, Trevor Mudge. Many students have worked on this project as well. Funding from GSRC and Marco. They've supported this from the very start. Chris Faulkner and ARM have done some prototype development. And then Bob Caldwell, who was the architect of the P-Pro architecture, which became the Pentium 2 and 3. He came up with this name, so I acknowledge him as well. All right, so what is it that we're trying to address with better than worst case design? There's a lot of challenges in hardware design that make it particularly good time to start thinking about how to design stuff that works most of the time with some guardians that can tell us when it's broken. And these are, in particular, what I saw at Intel was design complexity. The sheer volume of transistors and intellectual effort that goes into these designs makes ensuring their correctness really kind of a game of chance. There is no design out there that's fully correct. They all have bugs in them. And the verification process is trying to minimize the risk that there are some really bad bugs in those designs. It'd be nicer if we could raise the game there and actually build designs that we knew were fully correct. At the same time, there's a lot of threats at the hardware level in terms of silicon faults in the form of transient faults, which occur when natural radiation sources interact with very, very small transistors. Very small transistors have very little charge in them, and they can be affected by natural radiation sources like alpha particles and neutrons. And this is becoming more of a concern as we continue to shrink these devices that make up our silicon implementations. So this is another reason why it'd be great if you could build a piece of hardware that worked some of the time and there was something reliable that could fix it if the train came off the tracks. Another really interesting aspect of extremely dense silicon that we can really do some good with this style of design is something called uncertainty or variation. It turns out that as we sort of move on towards the end of the silicon roadmap, eventually that road ends. Eventually we go from silicon to something else, either bigger chunks of silicon or some other technology like a carbon nanotube-based technology or some other technology. Eventually we have to stop. Why? Because we're getting to these quantized number of atoms in the critical dimensions of transistors. Today the gate on a 65 nanometer silicon transistor is just tens of atoms thick, all right? And then the next generation is going to be 10 atoms thick. And the next generation, 2 atoms thick. And when you get down to that last atom, you don't want to split that last atom because that could be very dangerous. So at some point you got to stop. But what happens on the road to that last atom is variation increases. Making transistors in silicon is like baking. They put it in the oven and they put a lot of, mix a lot of materials in and they bake it. And every device is a little bit different. There's variation. The dimensions of the devices, if you want to make a channel that's doped, you literally got to put gases with boron atoms that go into the material. And if there's only a few atoms in that channel, then if there's only 10 and the variation is 2 atoms, the degree of variation in that particular device is very large compared to a previous generation, which maybe had 1,000 atoms, and there were 2 variation. So what you see as you go down to smaller and smaller devices is the range of performance of those devices increases. And so one way to address that is to be very pessimistic about your design and assume the very slowest transistor for your entire design. And you end up with a very slow design. What it would really be nice is a design that was a little more introspective, could kind of push the envelope, and when the envelope got broken, could back off. But in order to push that envelope, you need to detect when something's broke, when you've gone too fast. And so these kind of mechanisms can really address this uncertainty. And then finally, power demands. It's really the case today at all levels of design. Power is a primary aspect of design. In embedded systems, it defines how long you can run in terms of battery power. In high-end systems, it determines your maximum performance because cooling limits are being hit on all the high-end designs today. So you can run as fast as you can cool the heat you generate from running that fast. If you could cool it faster, if you had a better refrigeration technology or lower power devices, you would end up with a faster design at the high end. So how do you make faster? How do you deal with power problems? The number one way to deal with power problems is you lower voltage. Lowering voltage gives you this quadratic return in energy reduction in power. So if I cut my voltage in half, 1/4 the amount of energy and power generated. But what you end up with is you lose all these safety margins, these voltage margins that are put there because of noise, transient effects, etc. And so it'd be great if we had a technology that would let us push voltage to the absolute minimum, and if something broke, we could fix it. So again, technologies like better than worst case design can really handle this kind of stuff too. So there's really a multitude of things we can address with this style of design. So let's look at what better than worst case design is. But first I want to beat up on traditional worst case design. So here I've got my complex design here, this puzzle of a mess that I want to design. And the way I would do that in the past is I would sit down, I would take some high level specification, and I would design it at a low level and synthesize it, produce all the transistors, etc. And then I would say, what I would do design time verification. I'd make sure there's no bugs in this. Fully test it. Well, I really can't fully test it, but I'll test it to the best of my abilities. And I would optimize it at design time. I would assume the worst case conditions, worst case temperature, worst case noise sources, worst case variation, etc. And in this process, I would end up with a fairly high time to market because I have to make sure there's nothing wrong with this design. It's absolutely correct in terms of its electrical and functional characteristics. And then I'm probably going to use some very worst case assumptions about the temperature that it operates in, the amount of noise on the voltage, the amount of variation in the design. I'll look at all the worst case circuit paths to determine how fast I can run it, and I'll end up with a fairly low performance design or a very high power design. If I want to get a design to go faster, I just raise the voltage, more power, or if I have a fixed voltage, I just run it slower. So it's a costly approach that becomes more costly with all these trends I showed you on the previous slide. Here's better than worst case design. We still build the same exact big conglomeration of complex stuff, be it a microprocessor, or a crypto engine, or whatever. But I also add another piece of hardware. This thing's called the checker. The checker is going to monitor how this thing interacts with the outside world. And it's going to validate whether or not its interactions are correct. And if it finds an interaction that isn't correct, it's going to stop it, and it's going to fix that interaction. Now, this is what we call runtime verification, because this thing can actually fail. Stuff can be broken in here in very fundamental ways. There could be a design error in there, which produces a bad interaction that this thing detects and fixes. All right? Now, how does it do that? That's the rest of the talk. Okay. So, what you get with this runtime verification is you sort of lower the burden of correctness on this part of the design. It's not necessary that this design be correct all the time. It turns out when this thing's got to correct for this part of the design, it's fairly slow. So you want to make sure that most of the time it's correct. So you have a burden of making sure that it's wrong very infrequently. But there's also other cool things you could do. Let's say there's some aspect of the design that's insanely complicated to design and is rarely used. You can actually leave it out of the core of the design. Let me give you an example. When I worked at Intel, I worked on the memory scheduler. And the memory scheduler is this big, huge box. I mean, you could put your finger on this box on the die. It's so big. And what it does is it orchestrates the communication of loads and stores when they execute out of order. Now, a major fraction of this design is to implement the case when someone defines virtual memory synonyms that communicate through physical memory, and you have to do this in the box. And what if someone stores a word in a virtual address and then reads a byte from the middle of it at another physical address or another virtual address that doesn't match? It's got to detect all those scenarios. You can actually delete that kind of junk out of your main design as long as your checker can fix that problem. Now, the burden on the checker is we want to do that without as much complexity. So I'm going to show you today that you can actually do that. Checking is fundamentally easier than making a high-performance, correct implementation for all this stuff. And I'll show you some examples of that. Well, when I'm able to delete stuff from that complex design and tolerate some bugs in it, so maybe I don't have to spend 6 months verifying it, I can actually reduce my time to market. There's actually an opportunity to design stuff faster. And then, in addition, I can apply something called typical case optimization to this, where what I'm going to do is I'm going to optimize this core design for the way it will typically operate. So, for example, instead of building the adder to have the best worst case latency, I'll build the adder to have the best typical case latency. So that when the system tunes itself to the amount of energy or the frequency that it can run at, it'll be optimized for the way it operates most of the time. And I'll show you an example of this today too. But what you get out of this is you can get some really great performance gains. So here's an idea that can reduce time to market and give you performance advantages at the same time. And the way it does is by unshackling this big part of the design from correctness. This is performance. Correctness is concentrated on this checker. So now I want to show you a couple examples of these type of designs, just to give you some intuition on how this might be done. It's something that isn't automatic. You need to take a look at a particular design to come up with these checkers. There's a lot of intellectual effort in doing that. So the first design I want to show you is something called DIVA, which I did. This was the first design I did back in '99. And DIVA is sort of the sort of the ultimate end goal of checkers. It's a checker that can check everything on a microprocessor. So here's a big complex microprocessor. They have things like, high bandwidth front ends, dynamic schedulers, multiple physical resources, and register renaming, all this other junk that's inside there for performance reasons that creates these very complex microprocessor cores. And one thing they do is they speculate a lot. So these cores can run instructions all out of order, and then they decide if the guesses they made were correct. And the guesses are on, what data you're going to access, what direction of the branches, etc. And then at the very end of these pipelines is something called a commit stage. The commit stage is where you reorder all the instructions back to the original programmer's order, and you drop the register and memory results into memory in the original order that the programmer requested. Because experience has shown that programmers really like it when instructions execute in the order that they requested. It's a plus for a design. So that's how you get the benefit of all this reordering for performance. But then you get the programmers you can interrupt the processor, and it looks consistent with the original program. So what we do is we stick a checker stage right before that commit. And what the checker stage does is it asks the question, is the result of this instruction correct? And is this instruction at the right address? And is it the right instruction bits? And did it get the right inputs? So is the communication, computation, and control correct for this particular instruction? And if it is, it lets it retire. If it's not, it flushes this core, just throws away the work that's been done here, and and then fixes the instruction. I'll show you how it does that. Now, this thing can tolerate any manner of problem inside this part of the design. It can tolerate a design error. Let's say somebody got forwarding through virtual address synonyms in the memory scheduler wrong. It'll fix it. So a bug in the design will be repaired. It'll tolerate a transient fault. Some little piece of alpha particle hits a cell and changes a bit in a data value. It'll fix it. And etc. But as long as this is reliable. So let me show you how that particular component works. Yes.
Results of arithmetic.
Pardon?
Correctness of the results of arithmetic.
I do. So here's the secret. What's in that box is another processor. All right? And this is what, I gave my secret away too early. I just want to show you that that's my complex design, and that's my checker, right? So same basic model. What's in the box? Another processor. It's another processor that lives in a pristine world, which is the world of lots of hint information from the main processor. So, when I try and motivate, how would this thing work? I ask people, let's say I could give you a predictor that would tell you your branch directions with great probability. It would tell you your input values with great probability. It would tell you which addresses you're going to touch in memory with great probability 50 cycles in advance of executing. Now that great predictor is the other processor. It sends all this information to this processor, and this processor uses it to keep itself very, very simple. So this is a simple 5-stage processor. It has a fetch stage with a small instruction cache. It has a decode stage with a register file of its own. Has an execute stage with its own functional units, has a mem stage with a very tiny data cache of its own, and then a commit stage. So this is on the order of complexity of what we teach our students in our senior undergraduate level computer architecture course. They actually go and design one of these things. All right, but this one's a little bit different. It's different because all the stages occur in parallel. The reason why they occur in parallel is because the core actually sends us a bunch of information that allows checking to proceed in parallel. And this is really a fundamental advantage of checking. When you're checking something, you know everything about everything So the individual serial components that you would normally need to do to check can all be in parallel. And as long as you don't let, as long as your decision is the conjunction of all those tests, you can do all those tests in parallel. So for example, this stage, actually what it does, it checks. It doesn't actually do the fetch of the instruction. It just takes the address that that it knows the instruction should be at, fetches from its tiny I cache, and then compares the instruction to see if it is the same instruction. Did it fetch the right instruction bits? Actually, let me go to the next slide. This is called the check mode. Now you can see here that all I'm doing is configuring these muxes on the input here. In check mode, it's just checking to see if the instructions are correct. So it takes the core PC, fetches the instruction from its little I cache, and it says, is the instruction that the core executed the same? So did it get the same instruction? Bits. It takes the core instruction, which it doesn't know is correct, but uses it to fetch from its own private register file. And it takes the results from that, and it says, are these registers the same as the one the core got? If it is, it says, yeah, it's correct. It has the right communication. The core registers are actually, the register to fetch are sent from the core to this stage, and it re-executes your instruction, and based on that, checks to see if the result from the core was correct. Can do that in parallel as well. And then finally, if the result of the computation was an address for accessing memory, it accesses its data cache, checks the result to see if it's the same. So it's doing basically all the work that the core did over again and comparing to see if it's the same thing. All right. And if all four of these tests are the same, then it commits the result. All right. Now, first I want to answer the question, what if the results are different? If the results are different, if any of these things don't match, then that means something happened in the core. They either got the wrong PC, control was wrong, got the wrong instruction, its memory system was messed up, got the wrong registers, its register forwarding mechanism was broken, or it got the wrong memory address. In that case, or my checker's broken, but I'm telling you why my checker's not broken. In that case, we just reconfigure this pipeline by selecting the top inputs of the muxes, and we just execute one instruction through the sequence, and it's a very simple non-pipeline processor. It takes the result of its fetch, sends it to decode, sends it to execute, and then retires it. So it's very simple little design that can finish one instruction and revokes that right from the core and gets the core started on the next instruction. So normally it operates in check and then switches to this recovery mode. Yes?
Okay, so what we've just done is told the big core, you're out of your mind.
Yeah.
How expensive is it to give it back a mind that go forward?
Yeah, you got to get state back.
Yeah, do you have to reset it? Do you have to throw out how much state you have?
Yeah, it's very expensive. So what we do is we've got a couple of heuristics for this. First, we just flush it. If we get another error soon on, then we'll resynchronize its registers. If we get another error soon on, then we'll flush its caches, and at that point it'll
We just aggressively do more and more drastic things.
So who handles the cache miss for these little caches?
Yeah, these little caches. Now, so I want to ask, so the question I always get here is similar to that one. Like, how do these, why do these caches don't miss all the time if they're tiny, et cetera? Or another question I get all the time is, if this processor is so efficient, why do you need the main processor? And the answer is that there's a symbiotic relationship between these two processors, which allows one to be simple and fast, and the other to be complex and not fully correct. And it's a recognized phenomenon in computer architecture called slipstreaming, where two processors can leverage non-binding information off each other. But the idea is the same as in car racing. So I got two cars here. Right? This car is driving very fast, and if you've ever watched like car racing, you'll notice they always go in a long line, because the front car will be accelerating the air that the later cars will then be able to drive in with using less energy. And in auto racing, it's all about getting as far as you can on a tank of gas at the maximum speed. So it'd be nice if I could do that. If I could use my complex processor to allow my other checker processor to run with less energy would be nice, but what I really want is something a little more reliable there, like my Volvo. Now the Volvo could keep up because it has less resistance, so it needs a less powerful engine to follow this sports car because it only follows directly behind it. And that's exactly how this system works. This main processor does the heavy lifting of figuring out what are the branch directions, of figuring out what memory is going to be touched. And it sends non-binding information to this checker processor. Every time a new element is touched in memory, we preload it into the checker processor. Yeah. So the checker processor never gets cache misses. And when you think about it, what is everything we do in computer architectures for that causes complexity? It's to tolerate memory latency. That's half the problem. The other half of the problem is exposing parallelism. So things like dynamic schedulers are there to expose parallelism. How do you expose parallelism in the checker? Checking is fundamentally parallel. I know the results of the instructions I'm computing after and before me. I'm just checking so I can do everything in parallel. So in this processor, I have unlimited parallelism and I have no cache misses. That equals simple processor.
So what in the diagram we had for the checker, you were only showing architectural state flowing in, but you're saying there's extra state going on the side saying here are the addresses and data that go in your cache.
Yeah, so basically what happens is the L1 in this snoops off the miss stream from this one. But we also did another thing. We send the addresses in a queue to the L1 of the checker, and the checker actually rearranges its LRU bits based on future addresses. And it can actually simulate Belady's replacement in its cache. It knows what we'll touch in the future and doesn't kick that out of the cache.
So what is the consequence of a cache miss on the checker?
Just locks the pipeline up. It's a blocking cache.
So basically just delays the commit step.
And then the ultimate cost of the checker is what it does is it delays retirement in the core by at least one cycle. And if there's a cache miss, then it's 16, 32, whatever that is. And that puts pressure on the speculative state resources of the core. And when the speculative state resources of the core fill, then the front end's got to stop, and then it stops the core. So there's a little bit of a performance cost there in that there is some back pressure put on speculative state resources. But it's fairly low. We did simulations on this, endless simulations, and it's about a 3% slowdown with a very simple checker on the back end. And we actually did a physical design of this checker. We did a physical design for a checker that was matched to an Alpha 21264 processor. It was a fairly high-end processor. And in the same technology, the checker is about 6% the area of the processor it checks. So it's a fairly low-cost, small mechanism to do that. And in fact, we were able to put full BIST on this checker. And so we knew there was no physical defects in it, which you can't actually do for a big complex processor. So any defects that were not testable in the big processor, if they created a design fault or a bad computation in the core, would be corrected by the checker. Another thing we were able to do with the checker is do a full formal verification on it. And the reason why we could is because we actually did model checking on this thing, where essentially what we did is we posed the problem. If we have our processor and we don't specify what program it's running or what its current state is there ever a time when our reference model, which was just a state machine that implemented the instruction set, deviated in terms of function? So you can actually give this problem to a SAT solver, and the SAT solver will try to find the code sequence and the initial state of the processor in which they would deviate. And if the SAT solver comes back and says there is no case where this would happen, you have a formally verified design. That this design, under all circumstances, will match your reference state machine. Now, in a normal processor design, you can't do this. It's an intractable problem because of the amount of state. The Pentium 3 had 50,000 state bits in it. It's intractable to say, SAT solver, is there any combination of these 50,000 bits which will differ from this x86 state machine, for example? Pardon?
Would never try to verify the real thing. You verify some abstract model of it.
Right. Well, we have a nice abstract model here because this is where the processor is. What's the processor in this formal verification? The processor is unreliable. It can send any result to the checker. So it's an unspecified input. So this huge design, which was formerly intractable to formal verification, we lop it off and say, it'll say something. We don't know if it's right. And it makes the formal verification concentrated only on the checker. And that was tractable, and we were able to do this for the alpha processor, guarantee that the checker never produced a bad result, a functionally bad result. So that was a great result as well. I did that with Karim Sakala at the University of Michigan.
When you say small data types, do you mean your registers are not 32 bits wide? They're 2?
Oh yeah, we used standard abstraction techniques where from the formal verification, there's a fairly large body of work that's been done on how to take a microarchitecture and first prove that this design will produce the same results with 1-bit data types as with 32-bit, and then they collapse it down to 1 bit, and then there's sort of a sequence you go through. And normally you end up, at some point you can't go any further because the simulation would run forever. But we actually got through the whole process.
I think usually the model checking can prove the correctness of the logic, but how do you deal with the hardware, for example, transient errors in the checker, which is not a logic error?
Yeah, well, that's a good question. I don't cover that in this talk, but you can actually deal with transient errors in the checker. So a transient error is when some alpha particle comes and hits a transistor and produces a bad result. So think about this.
You can't really tell an error in the checker from an error.
Right, exactly.
You restart.
So what you do is you just run the same results on the checker again. So anytime you get an error, you say, was this a fault in the checker or a bug in the design or a transient in the design? The way you answer it is you just take the information that all we do is we take the information from the latches of the checker, we cycle them back to the beginning and run it again. And if it disagrees with the core result again, then it was something in the core. If it disagrees with itself the second time, then it was a transient in the checker and we use the second result. The only thing we can't catch is a transient in the core or a bug in the core and a transient in the checker, but that's a product of 2 extremely unlikely events, and we erase that from our failure model.
So presumably you can't catch the very unlikely transients in the code that's switching the muxes for the checker, but I guess you make those out of really big sloppy transistors.
Oh, yeah. Well, I've got a paper on that, too, where you can actually use triple modular checkers.
Well, it seems like I guess what I'm saying is you could go ahead and use the worst case design for the very tiny circuit that's left.
Yeah, but then what you get is so one of the things you learn with fault-tolerant design is there's no such thing as 100% reliable. But your scenario is, there's a big target over there and there's one atom I got to hit with my dart.
So this one probably is
So
you don't care.
your coverage is not compromised by that particular case because it's so unlikely it'll ever happen. All right, so now I want to talk about another design called Razor, which is also some more recent work. Razor is a follow-on to the DIVA work because when the DIVA work came out, I went to industry, I went to Intel, I went to AMD, I went to IBM, and I gave talk after talk after talk after talk, and everybody said, this is an awesome idea, we'll never do it. And the reason why is because it was just too much to add a bunch of hardware to make sure our designs are correct, because we think we can do a correct design, et cetera. So I started going in 2 different directions at the same time.
You think that's too old?
They don't care anyway, because if they get the wrong answer, we get blamed.
Yeah, exactly.
Do you think that's too old?
What? Oh, no, that's changing. But
Changing, huh?
at the time, it was really the case that people didn't think they would put they would change their design. So I started 2 initiatives. One initiative was something that we talk a lot about in the GSRC, which is this notion of value-added resiliency, where if you can detect and correct bugs and you add hardware to do that, what else can we do with that hardware? Well, we can overclock, we can undervolt, we can reduce time to market. There's a lot of value-added capabilities you could generate with the same infrastructure. So we started looking at that possibility. So Razor is not about correct design. It's about running with the absolute minimum amount of energy in a design using the same basic mechanism. And then the other thing I did is I went a baby step. Razor is much simpler than DIVA, and it's a tiny little step in the direction of DIVA. And what it is it's an approach to let the circuits themselves in a design of a microprocessor determine the minimum amount of energy that they need to operate on. So a couple years ago, a grad student of mine, Dan Ernst, did a motivating study where we took an FPGA board, hooked it up to a voltmeter, and started dropping voltage on this thing to figure out how the circuits failed. And this is a Xilinx part that's got a lot of DSP components in it. It's got some big multipliers on chip. And what we did is we built this circuit on the FPGA. What this is just a multiplier that takes two random inputs into the multiplier. And this particular multiplier can operate at 1.5 volts at 90 megahertz. And so it produces every, 1/90 millionth of a second, it produces a 36-bit result, which we compare against the results of these two multipliers. Now, these two multipliers run at 45 megahertz. They run at half the speed. And half the speed means they're going to be able to go to much lower voltages than a 90 megahertz one, which is really pushing the envelope. So we alternate the two results here. Every cycle we take a new input here. Every cycle we take one here. Next cycle we take one here, then we pick them off. Every other cycle, compare it to this one. And so two 45 megahertz multipliers check the results of a single 90 megahertz multiplier. Now, the reason why we do that is because we're going to drop the voltage on this circuit, and we want to make sure that our checkers are running reliably as this starts to fail. And the way you do that is you run slower, because lowering voltage means slower circuits. So by running at half the speed, we can run to much lower voltages. So here's what happens when you lower the voltage on that 90 megahertz multiplier. So what happens is you lower the voltage, and first thing you notice is nothing happens at all. It keeps working to lower and lower voltages. In fact, it doesn't start to fail until this voltage. This voltage right here, 1.69 volts, this is oh, I gotta put my power on here. I need some voltage. That 1.69 volts, that's the voltage that the Xilinx timing analyzer says, thou shalt not run this design below that voltage. There we go. And so you're not, they don't guarantee any reliable running below that. But you can actually lower the voltage all the way here to 1.52 volts before any errors occur. Now, why is that? They put margin in. They put design margin in. They put make me feel comfortable design margins, probably 10%. They put in temperature margin. These parts, they're designed to run at 90C. It wasn't 90C in the lab that day, right? They put in voltage noise margin. There's variation on the voltage. They put in process variation margin. They know not all their chips are going to be sweet, fast chips. Some are going to be slower. And so you get a lot of margin that you can lower it. And that's why you can overclock processors. That's why you can go out buy an AMD 1.6 gigahertz processor and run it no problem at 2.2 gigahertz because of all the margins for temperature. That's why when you go to the overclocker website, they're always talking about the great cooling systems that they want so they can run faster. Because the lower they can push the temperature, the faster the circuits will run. But look at this. At the first error point, there's only one bad multiplier every 20 seconds. So it's not failing very much. It's just failing when it hits that one long path every once in a while. And then you get a kind of an exponential increase, a log scale. You get an exponential increase in the failures. But look at this. Let's say you could automatically tolerate 1% circuit failures. You know, that's my job. I'm going to figure out how to do that. At 1% failure rate right here, you're 22% energy savings from the point of first failure. You're saving 22% energy over where the thing first failed if you can just tolerate 1% error rate.
Need more than that over the spec.
And then 35%, yeah, thanks. 35% over that, thank you. 35% over that ridiculously conservative point that they first spec'd. So basically what's happened is there's a lot of energy laying on the table there. All we need is a mechanism to find those timing errors that occur and fix them when they occur. So that's our next better than worst case design. Oh, and here's an interesting thing. We were shooting random vectors into that circuit. What if you shoot real data into a circuit? This is a Kogi stone adder running at 870 megahertz at 27 degrees Celsius. And the blue line is random data. And you can see that the error rate, as we drop below 1.8 volts, raises exponentially. All right? Well, the two lines below it are data from some spec benchmarks. That's real ads for a real program. And what you see is they rise exponentially too, but they rise a lot later. In fact, you get about a 200 millivolt margin in this experiment. And the reason is because random data hits those long critical paths with great frequency because it's agnostic as to what is being computed. But real data is adding small numbers, subtracting small numbers, and it tends to be, for an adder, congregated to the shorter circuit paths. So your error rates rise much slower. So there's actually, not only is there margins in the design from temperature and process variation and safety margins, but there's data margins for many elements for many components that we build. So, working with David Blau and Trevor Mudge at University of Michigan, with Marco and GSRC funding, of course, we came up with this idea called Razor. And the name comes from the fact that Razor is going to shave voltage margins until there's none left. And so we came up with this approach. And the basic idea is we need a detector to find out when a circuit has failed, and that detector also needs to correct it. That's our checker mechanism. And what we use is a double sampling latch. This is a simple pipeline from a processor. It's an execute stage with an adder and then a mem stage here. And here's my clock cycle. So each clock cycle, the data goes from the input latches to the output latches and then to the next stage. Well, I run my clock cycle and I put a couple of inputs on the adder and I let the computation go for a full cycle. Right before the clock ticks again, the adder should have computed the result, which is available to the next latch. And then when the clock ticks, the latch will take the input and send it on to the next stage. Well, in this case, let's say I didn't have enough energy in the system, and it can't compute the right result in time. So it gets a bogus result at this main latch, and then sends that bogus result into the next stage of the pipeline. It starts working on that value. Well, what the Razor system does is it does something called time borrowing sampling, which is a fairly well-known technique in VLSI design. It comes out of the world of wave pipelining, where basically you let a little bit of stuff cook on the output of logic when you pump the next stuff in. And there's a few things you got to do in order to get this to work. You got to do hold times, et cetera, et cetera. But it's actually a well-known technique that can work pretty well. And we use that technique. We let the stuff cook on the output even while this starts computing on the next set of results. And we take a second sample a little while later in this thing called the shadow latch. Now, amidst all of this extra cooking here, we're still computing on a bogus value here. The pipeline's doing bad stuff. We'll fix that in the microarchitecture. When we take that second sample, we design that second sample and that second latch using the most conservative design techniques possible. Worst case temperature, worst case process variation, worst case noise margins, safety margin, etc. So we know for sure that the second sample at this latch is always correct. If these two don't match, we then have to recover the state of the machine. And we do that by recycling the data back into this main latch and letting this stage recompute again on the correct data. Now this is just like my original design where I had this complex component up here, which is my main pipeline, and now my checker is this simple little latch here doing a second sample on the data. The checker is built more reliably than the main pipeline, so if it disagrees, it'll override what the main pipeline is doing. Now this thing can actually find and correct timing errors. Now that's useful because as we drop voltage, what's going to happen is all the circuits get slower. We'll save tons of energy, but everything gets slower. And at some point, those circuits will be too slow to finish within a cycle. And then these Razor detectors will start going, this is broken, this is broken, this is broken. And let's see how we can utilize that. But before we do that, we've actually got a problem in the pipeline. We forwarded bad data to the next stage, and we need to recover the state of the program. Now this turns out to be something that's very easy to do in microarchitecture. It's simply misspeculation, where instead of dealing with misspeculation of an instruction, we're now dealing with misspeculation of timing in the circuit level. The result is the same. We've got a bogus computation in the pipeline, and we need to flush the pipeline. So I can show you an example of this, how we recover in our prototype. In this stage, instruction 2 failed. When instruction 2 is giving bad results to mem, the shadow latch in this stage will determine that it was a bogus result. At that point, we have to cycle the correct result back into the Razor latch so that mem can get the correct result, and we send a signal on to the next stage that say whatever you did in this cycle, ignore. So we have one cycle to tell the next latch it was bogus results. Then we have this thing called the flush train, which is going to go all the way back to the beginning, flushing all the instructions behind instruction 2. And the reason why it needs to do that is because we may have sent a bogus result to mem. We may have also forwarded a bogus result back in the pipeline. So we just flush all of those instructions. And when we get back to the original part of the pipeline, we restart the instruction after the one that failed. Now that's a really cool result for Razor. What it means is Razor doesn't have to redo the instruction that failed. It gets the right result from the shadow latch. And because of that, we don't have to do crazy things like raise the voltage to finish the instruction correctly or cut the clock frequency or whatever. We can continue to push through errors and operate in the presence of errors. And you'll see in a little bit, that's actually a big advantage for saving energy. Okay, and then 3 comes back in the pipeline, and we're recovered the state of the pipeline. So we went back to industry and said, you got to check out this idea. It's an awesome idea. Showed them the idea. Look how simple it is. And they said, that's an awesome idea. It'll never work. And so at that point, we decided we got to do a prototype and build a chip that actually demonstrates this technology. So we, working with David Blau, who's had a lot of experience in VLSI design in his work at Motorola, we designed this test chip, which is a simple 5-stage pipeline for the alpha instruction set. It was manufactured by Moses, and here's our little test setup. We came up with a really great little test environment where basically we just built the chip and hooked it up to a DIO card that was on a laptop, and basically using programs written in Windows, we're able to simulate the clock and scan in and out data and do all our experiments on this. It was a real nice platform that we developed. And then we put it to the test. What we did is we built this closed loop system. We took a little voltage regulator, and we would monitor the rate of errors coming out of the processor. And what we did is we tried to target using this control loop. We tried to target a reference level of errors. Why is that? Well, you don't want 0 errors in your pipeline, because 0 errors in your pipeline means either you're at the perfect voltage or your voltage is too high. You've got too much energy. What we really want to do is we want to start lowering the voltage. Lower, 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 until you get to the point where it's failing a tiny amount. And then if conditions change, like it gets colder, those errors will go away and you'll know to drop voltage more. Or if it gets warm or the workload starts executing longer circuit paths, your error rate will go up. and then you raise your voltage. And you do that with a simple proportional controller. It has a reference error rate, which in our case was 0.1% errors. 1 out of every 1,000 instructions should fail. And if it was above that, it would lower the voltage. And if it was below that error rate, it would if it was below the error rate, it would lower the voltage. If it was above the error rate, it would drop the voltage or raise the voltage. Okay. And then what you see is this is the actual chip running, where the blue line here is the voltage and the purple line is the error rate. And you can see if the error rate's low, the voltage is low. If the error rate goes up, the voltage goes up until the error rate goes down again, and then at some point it drops the voltage again, and you get this simple proportional controller. This is just a little test program that switches between heavy computation mode with long circuit paths and a mode where it uses short circuit paths. So it responds to the amount of energy the system needs. And then when you analyze this thing, here's what happens. On this axis, I've got decreasing voltage. On this axis, I've got energy. So what happens when you take your Razor system, which nominally runs at 1.8 volts, and you start dropping the voltage on it? Well, you get this quadratic reduction in energy. If I cut the voltage in half, I have 1/4 of the energy. And it continues to drop as I drop the voltage. Well, we had to add a bunch of hardware to do this Razor stuff, so our real design actually uses a little bit more energy overall because of those Razor latches. There's an overhead. Now, eventually the thing fails, right? It gets to the point where it can't run anymore, and the Razor latches kick in. Now, when a Razor latch kicks in, it's got to flush the pipeline. It's a very expensive event in terms of energy, because you've got a bunch of cycles that you inserted into your execution that weren't there before. And so the amount of energy for recovering goes up proportional to the error rate, which is exponential. So that goes up pretty fast. But remember, it starts out at 1 every 90 million. It starts out very low, but it does rise very quickly. So you see this wall of energy required to recover. The total energy of the system is the sum of these two lines. Now there's one other thing that you got to remember. There's a performance cost associated with recovering that pipeline as well, because when you flush a pipeline, you lose throughput and the program runs slower. So there's also pipeline throughput is dropping as your error rate is going up. But the end result for many of the programs we looked at, you could pretty much cut energy in half with about a 1% reduction in throughput.
So what was the error rate?
The error rate?
At that 50% energy savings.
Yeah, it's usually between about 0.1 and 1%. It's low. And we actually tried to come up with really clever control systems that would try and walk as close to this wall as possible. But it turns out staying back here is almost the same amount of energy savings. Being at a 0.01% error rate is only a few percent less energy savings than being at a 1%, so the optimal point. And so you build a control system that's really stupid and stays really far away from the wall, and it does great. So it's, that's one of the nice things about this steep wall here. You just stay far away from it.
I'm worried about the stability of a control system.
Yeah. Well, it turns out that moving voltage is a very long and painful event in terms of processor cycle times. So you tend to have a very long time constant in it. And because you're so far away from that wall, because you're operating a supply voltage that's sufficiently high to not really aggravate that error rate, and because of the type of things it takes to change that error rate, changing temperature, changing workload, the response has actually been very good for the programs we've looked at.
So Todd, you build your prototype, you go back to the industry, they buy off on it this time.
Yeah, I think they're buying off on it. I think there's Intel, ARM, IBM are all seriously looking at this technology. And I think this one might stick in some form. So I really became sold on building stuff after this particular experience. Although I don't recommend it to anyone. If you're interested in more information about this. The March 2004 edition of IEEE Computer Magazine was dedicated to better than worst case designs. And there's a bunch of other stuff in here as well as Razor. So you can see, what are some other type of things people are working on. And in fact, there's another GSRC project in here. Naresh Shambhag from Illinois presented his work on algorithmic noise tolerance, which was a really clever idea. The idea there is do something similar to Razor for digital signal processors. But in the digital signal processor, a circuit error, if it's well placed, that is in the least significant bits of the computation for the signal, you can actually write off as noise. And you don't need to recover to a certain extent. It's a pretty clever idea at the application level. And it just goes to speak that, whatever you can do higher in the design stack, the cheaper it gets. So here's some interesting stuff to look at if you want to learn more. And I'll just spend 5 more minutes on another opportunity for better than worst case design. And I talked briefly about this, about typical case optimization. Imagine a Razor system where it adjusts the amount of energy in the system based on the workload, temperature, etc., based on that error rate it experiences. If you look at a typical adder, the way it's designed today, a very popular adder used in a lot of designs is a Kogi stone adder, which is optimized to minimize the worst case delay through the adder. And the way they do that is by providing dedicated carry propagation paths for almost any propagation you could possibly imagine, from bit 1 to bit 32, from bit 2 to bit 32, etc. It's a very heavy piece of logic, and it turns out that the most optimized path, the one that gives it the greatest amount of value, is the logic chain that goes from the start to the finish. That's the one that's the most heavily optimized. And that happens when you take a 0 and subtract a 1 from it, and you carry all the way up. Okay. Now, if you look at the carry propagations in adders, it turns out that that long path is rarely exercised. So here's a 2-dimensional graph. This is the probability of the event on the z-axis. This is the bit position for a 64-bit adder, bit 0 to 64. And this is the carry distance. This is how far the carry propagation went. So if you have a 0 minus 1, the carry propagation is 64 bits. And as you might expect, because it's random data, it's agnostic about which bit position it is, so you see the same results for every bit. And it's quadratic, right? The probability of having a 2-bit carry propagation is half as likely as a 1-bit, right? So you see it drops off. The 1-bit propagations are fairly frequent, and then it drops off very frequent, and you don't see long propagations very often. So what that means is that the path that is most optimized in today's adders is extremely unlikely that you'll ever exercise it. Well, it's even worse if you look at real data. This is a bunch of spec data on the adder. And real data only uses the least significant bits with any probability, and the carry propagations are fairly low. In fact, there's one here that kind of spikes due to the stack, but in general, very, very short propagations in the least significant bits. So what we did is we redesigned the adder. We redesigned an adder that could do really efficient 6-bit propagations up through bit 9. And then above that, all it could do was 2-bit propagations. And then if it needed to have a longer propagation than that, it had a backbone that could finish in about 16 cycles, which was a kind of a carry look-ahead adder in the back. This would be a horrible design to put in a traditional design because it has really bad worst-case latency. But its typical case latency is great. If you stick it in a Razor design, Razor will detect when it has to execute that long carry propagation and will recover the state of the pipeline. In the normal case, it'll drop voltage as far as it can to the amount of energy needed by these typical case optimized paths, and we found some great results. A Kogi stone adder, worst case latency of 8 gate delays for the design we looked at. It was double for our optimized adder. But look at the typical case latency, 5.8 gate delays for the Kogi stone, 3.03 for our optimized adder. So it almost 40% reduction in the typical amount of energy that it needed because we designed circuit paths that were optimized for the typical case rather than the worst case. So the basic thing I want to show here is that if your design can tune itself to the workload, temperature, et cetera, it really gives you an opportunity to rethink how you build logic components and functional units and designs overall. So, to conclude, better than worst case design is an approach that abandons traditional approach of worrying about all the worst case scenarios and instead combines a complex design with a checker. The complex design is worried about performance, meeting the goal of speed and energy. The checker is chartered with the job of correctness and reliability. We looked at two designs, that DIVA checker, which can fully check a microprocessor, and the Razor logic, which just does timing errors and can be used to reduce the amount of energy. And there's some interesting opportunities to rethink how logic components are implemented in this Razor environment. And then finally, since I'm visiting Microsoft, and I know I'm going to talk to a lot of people, I just wanted to give you one slide that shows you some of the other stuff I've done. So as I meet with people today, we could talk about that stuff. Thing I'm probably most notorious for is the simple scalar tool set, which will not die no matter how much I try and kill it. I worked on that. So, and simulation has been a long time interest of mine, of course. Another project that I'm real proud of is the Subliminal Systems project, which has made some of the most energy efficient processors ever made. And the way we do this is by never turning on any transistor ever. There's this sort of, as you lower voltage, you reduce energy, right? Well, you get to this point where you hit the threshold voltage of a transistor. That's the minimum voltage before it turns on. So if you want to lower voltage beyond that, you never turn on your transistors. So you just keep lowering the voltage. So how do you compute without turning on transistors? You modulate leakage. Transistors are always on a tiny little bit. And so we built this design that computes based on modulating leakage at hundreds of millivolts. And we built a prototype. This one right here, the Subliminal 1, operates at about 1.2 picojoules per instruction, which is about 10,000 times less energy than a modern microprocessor. And the Subliminal 2 operates at 650 femtojoules per instruction. That means it'll last 1,000 years on the energy in a AAA battery. So that's a fun project. Oh, 40 kilohertz. There's the rub. Not only when you go sub-threshold, super threshold circuit delay is proportional to voltage. It's actually an exponential decrease in speed as you lower voltage below because leakage is exponentially related to voltage. But it turns out there's a lot of applications, especially sensor applications, that don't need a lot of processing power. Like, how much processing power do you need to measure, an earthquake? You don't need a lot. Or the application we're working with we're working with the med school to build an intraocular pressure sensor. So it's a MEMS sensor with a processor and a solar cell that scavenges energy from inside the eyeball. It only has to run, it does very low computation.
You write science fiction as well.
So you power it by blinking of the eye?
Well, it has to have a battery in it too, because when you go to, we could say that you can't sleep with this device, but it's got to be able to hold the state overnight. And then the Bulletproof project, which is also sponsored by GSRC, is a project that we started last year to build defect-tolerant microarchitectures. And the idea here is we want to address some of the late-stage silicon problems in that it's likely in 2 or 3 generations of silicon, you're going to have to deal with breaking transistors during the lifetime of a device. So how do you build low-cost resiliency in these devices? And we're using a lot of the same techniques that we developed for Razor and DIVA to do this, but now we have the added problem of repair. Because you can detect and correct for an error, but if it's a busted transistor, you're going to have a huge problem in terms of performance. So you need to diagnose and repair as well. So it's an added burden in the design. And then I've had some interactions with people in Microsoft Research on the Stone Shield project, which is a software verification project that I have. I tend to look at my research as error resilience research, circuits, architecture, but also I've worked in software verification for quite some time. I had one of the first papers in PLDI on software verification back in 1993. And this project is examining how can you utilize symbolic simulation to do security checking on programs. So it's kind of a supercharged simulation technique where we can compute with unbounded values. And those unbounded values are derived from the inputs of the program. And then once you compute on those, you can actually do things like memory access checking on these unbounded values, and they contain the constraints of all the checks that you've done to them. And you can actually figure out if a program could have a memory access fault without actually having exposed it. It's a pretty powerful technique. And one of my grad students, who's now at Seattle University teaching there, was one of the first people to do this semi-symbolic execution in programs. And this was really an offshoot of the simulation work we've been doing for many years. And then better than worst case design. Been working on that for many years. So thank you for coming to my talk. And then this is my favorite better than worst case design quote that I'll leave you with. Thanks.
Kind of like if you never miss a plane.
That's Mark Horowitz's quote, I've heard. Yeah. If you're never missing planes, you're spending too much time at the airport. Thanks.
All right. That's good.
Yeah.
You want it now? Or?
Yeah, yeah.
This typical case design rather than worst case design. Some of your examples remind me of asynchronous or self-time
Yeah,
techniques.
yeah.
So it seems that may be another way to get at the same kind of results.
Absolutely.
Any views on that? Or
Oh,
I'm sure you've heard
absolutely.
this before.
Oh, absolutely. So I consider Razor a semi-synchronous design. It has highly controlled asynchrony in that its asynchrony is limited to one particular component that's replicated throughout the chip. But it's still, the advantage over, it has a number of advantages over asynchronous design in that it still uses a synchronous design methodology to design it. So you're still working in a traditional synchronous design framework. And I know one of the big problems with asynchronous design is nobody knows how to do it. It's I mean, people know how to do it, but
Some people do.
the masses don't know how to do it. So, so it has that advantage over that. But it definitely borrows from that world heavily in that, like asynchronous design, it'll adapt to data, it'll adapt to temperature, it'll adapt to, to process variation as well. So I see it as a good middle ground between synchronous and asynchronous design.
Latch is really a completion checker, right?
It is a completion checker. Yeah, it is. Yeah, good observation. One thing that asynchronous designs can't do is speculate. They can't speculate on timing. They can go to that point where the first failure occurs and live in that place. Razor can actually go and say, we don't care about these particular circuits. We're not going to let the system run at the rate they want to run. We'll incur some errors when these occur. We really want to run at the rate these popular circuits want to run at. And I think there's a little bit of an advantage for that. Any other questions? Okay. Thank you very much.
All right.